Imagine standing at the edge of the San Francisco Bay on a foggy morning in the early 1930s. The Pacific Ocean surges in front of you with a power that you can feel in your chest. Beneath the surface, the water runs up to 335 feet deep. The currents twist and collide, the cold Pacific rushing in one direction, the fresh water from California's rivers pushing back. Tides rip through the narrow strait with a force that could sweep a grown man off his feet in seconds. Hands somewhere between you and the distant green hills of Marin County, separated by 1.25 miles of open ocean. Engineers were about to attempt something that the world's best bridge builders had called absolutely impossible. This is the story of how they did it anyway. How a structure once dismissed as a fantasy became the most recognized bridge on Earth. And how a team of engineers, divers, ironworkers, and cable spinners built a monument that would last for generations. For $35 million and 4 years of relentless work in the middle of the Great Depression. If you enjoy learning how the world's most incredible engineering projects actually work, consider subscribing. On this channel, we break down the science and engineering behind the structures that shape our world. The idea of connecting San Francisco to Marin County across the Golden Gate Strait had been floating around since the mid-1800s. After the California gold rush transformed the region into one of the fastest-growing economies in America, the land north of the bay became increasingly valuable, but to reach it you had to take a ferry. For decades that was fine. Then the automobile arrived. By the 1910s and 1920s, car ownership was exploding across America, and ferry lines were struggling to keep pace with demand. The city of San Francisco needed a bridge. The problem was that nobody could agree on whether building one was even remotely feasible. The Golden Gate was not like other waterways. It was narrow, yes, but it was also violently unpredictable. The winds above it could gust to hurricane strength. The currents below were among the most powerful on the California coast. The bedrock at the bottom was irregular and difficult to reach. And then there was the earthquake risk. San Francisco had been nearly destroyed by a massive quake in 1906, and engineers knew the city sat in one of the most seismically active regions in North America. To bridge the gate, you would need towers tall enough to rival skyscrapers, cables strong enough to hold tens of thousands of tons, and foundations built into the floor of an open ocean. Expert after expert declared it could not be done. One man disagreed. His name was Joseph Strauss, a compact, determined engineer from Chicago who had spent his career building drawbridges and movable spans. Strauss had never built a suspension bridge of any great scale, but he believed that the right design and the right team could conquer the Golden Gate. In 1921, he submitted a proposal to San Francisco city engineer Michael O'Shaughnessy, a hybrid design that combined cantilever trusses with a central suspension span. It was functional, if not beautiful. But more importantly, Strauss insisted the project could be built for $25 to $30 million, a figure far below earlier estimates that had run as high as $100 million. That price tag got people listening. The years that followed were filled with political battles, legal challenges, and fierce opposition from ferry companies, real estate interests, and skeptics of all kinds. But Strauss was relentless. He traveled the region, spoke at community meetings, lobbied politicians, and slowly built a coalition. In 1923, the California State Legislature passed the Golden Gate Bridge and Highway District Act, creating a special governing body to design, fund, and build the bridge. Over the following years, the surrounding counties joined the district, though not without resistance, and the long, grinding work of actually planning the project began in earnest. As planning advanced, it became clear that Strauss's original hybrid design was not going to work. It was functional, but it was also ungainly and visually heavy, a clunky industrial structure that would have looked jarring against the spectacular natural scenery of the Golden Gate. The final design that emerged was a pure suspension bridge, and it was largely the work of a New York engineer named Leon Moisseiff, who had helped design the Manhattan Bridge. Moisseiff introduced a concept called deflection theory, a mathematical framework that allowed the bridge deck to flex in the wind rather than resist it rigidly. The idea was elegant. Instead of bracing the roadway against the force of wind gusts, engineers would design it to bend and move, distributing stress across the entire structure. This made the bridge lighter, more economical and, crucially, safer in the conditions the Golden Gate was known to produce. The actual engineering calculations, which ran to thousands of pages, were largely produced by a senior engineer named Charles Alton Ellis. Working remotely by mail and telephone, Ellis performed extraordinarily complex structural analyses by hand. This was decades before computers existed, computing loads, stresses, cable geometries, and tower heights across months of exhausting mathematical labor. His work formed the true engineering backbone of the project. When the Golden Gate Bridge was finally recognized as one of the 7 wonders of the modern world by the American Society of Civil Engineers, it was as much a tribute to Ellis's quiet genius as to anyone else involved. The visual design of the bridge, the towers, the Art Deco detailing, the distinctive shape, came from a relatively unknown residential architect named Irving Morrow. Morrow's contribution is often overlooked, but it was transformative. He replaced the flat industrial surfaces of earlier tower designs with a system of vertical fluting that gave the steel a sense of movement and elegance. He redesigned the bridge's lighting, and it was Morrow who chose the now famous color, a warm orange-red officially called International Orange, after rejecting proposals for gray, silver, and even yellow. Morrow understood that this bridge would become part of the landscape. He wanted its color to harmonize with the red hills of Marin and the warm California sky, while remaining clearly visible to ships navigating through the famous San Francisco fog. The choice was inspired, and it became perhaps the single most iconic visual decision in the bridge's history. By the time construction contracts were awarded in late 1932, the country was deep in the worst economic collapse it had ever experienced. The Great Depression had left millions of Americans out of work. Jobs at the Golden Gate Bridge construction site were desperately sought. More than 3,000 workers would be employed over the course of construction, and for many of them, the work represented survival itself. Some reportedly waited at the site perimeter, watching for workers to fall, hoping to step into a sudden vacancy. The desperation of the era is impossible to separate from the story of how this bridge was built. Construction began officially on January 5, 1933. The first task was not the bridge itself, but the massive anchorages on each shore, enormous concrete blocks into which the ends of the main suspension cables would eventually be locked. The anchorages had to be excavated deep into the earth and rock on both banks. On the San Francisco side, workers blasted and dug into the hillside. On the Marin side, they carved out a pit in the rocky slope above the water. These anchorages were not just blocks of concrete. They were engineering structures in their own right, each one containing a web of steel cable shoes, anchor bolts, and reinforced chambers designed to absorb and distribute the colossal tension the main cables would eventually impose on them. The weight and volume of concrete involved was on the scale of building a stadium. Each anchorage took 3 years to complete and was finished in 1936, just in time for the cable work to begin. While the anchorages were being built, the even more difficult task of constructing the 2 main towers was underway. The North Tower, on the Marin County side, was the easier of the 2. Its site was on solid rock near the shoreline, and workers were able to excavate down to bedrock, build a foundation using poured concrete, and erect the steel tower sections above it. The steel itself, high-strength alloy steel fabricated at Bethlehem steel plants in Pennsylvania, was shipped by rail to Philadelphia, then by boat through the Panama Canal to San Francisco, and hauled to the site by barge. The tower sections were assembled on the ground and lifted into place by crane, with ironworkers bolting and riveting each piece into position. Each tower was composed of hundreds of open steel cells, stacked and connected, to form a structure that was strong enough to carry immense loads while remaining flexible enough to sway in high winds without failing. Each finished tower contained approximately 600,000 rivets. But the South Tower, that was a different story entirely. The South Tower had to be built more than 1,100 feet offshore, directly in the water of the Golden Gate Strait. No bridge tower had ever been built in the open ocean before. There was no precedent. Engineers had to figure out how to sink a foundation into bedrock that sat 35 meters below the surface of a body of water with brutal currents, regular storms, and extremely limited visibility. The solution was audacious, and it began with a structure called a fender. The fender was essentially a protective oval-shaped cofferdam built around the site of the South Tower's foundation, a reinforced concrete barrier about the size of a football field, constructed first as a shell and then filled with water to give it the mass needed to resist the current. Getting the fender built required workers to blast away surface rock on the ocean floor, drill deep into the bedrock with explosives, and pour underwater concrete using specially designed molds and funnels that allowed the material to flow into place even in the swirling water. Divers worked constantly, guiding steel panels and forms into position in near-zero visibility, in water so cold and fast-moving that their equipment was tested to its absolute limits. Every shift brought the risk of being swept away by a current that could overpower even the most experienced swimmers. Once the fender was complete, engineers faced one of the most demanding operations of the entire project, pumping 9.5 million gallons of water out from inside it. With the water gone, workers found themselves standing on the exposed ocean floor, surrounded by concrete walls, working to excavate the final meters to bedrock. The conditions were surreal. Seagulls swooped in to feast on the fish left stranded by the drainage. The smell of brine and wet rock filled the enclosed space, and above them, the Pacific Ocean pressed against the fender walls on all sides. The foundation was completed, slowly, painstakingly, and the tower sections began to rise above the water's surface. But before the South Tower was finished, the fender was hit twice. A powerful storm damaged it badly, requiring emergency repairs that added months to the schedule. Then, on a foggy night in August 1933, a cargo vessel traveling through the strait collided with the access trestle, connecting the site to the shore, destroying it completely. Workers were stranded. The damage took time and money to repair. These were not the last setbacks engineers would face, but they were among the most dramatic early reminders of just how hostile this environment truly was. The Marine Tower was completed in October 1934. The San Francisco South Tower was finished in June 1935. For a brief moment, the two towers stood alone across the water, elegant, orange-painted steel monuments rising 746 feet above the surface, the tallest bridge towers in the world at the time. And now the most visually spectacular phase of construction was about to begin. The two main suspension cables were the literal backbone of the bridge. Each one would need to stretch from its anchorage on one shore, rise over both towers, and descend to the anchorage on the opposite shore. Each cable would carry 6,000 tons of the bridge's total load, and each cable, when finished, would be just over 3 feet in diameter and roughly 7,600 feet long. The challenge was that cables of this weight and length could not be manufactured elsewhere and brought to the site. They were simply too heavy. Each one weighed 12,000 tons. There was no barge, no crane, no derrick in the world capable of lifting them into position. The cables had to be built in place, wire by wire, on site, across the open span of the Golden Gate. The company given the contract for this work was John A. Roebling's Sons Company, the same firm that had built the cables for the Brooklyn Bridge more than 50 years earlier. They had spent decades refining a technique called parallel wire construction. The basic method was this. A single steel wire, slightly thicker than a pencil, was carried back and forth across the span on a spinning wheel mounted on a traveling trolley. Each wire was looped over a massive cable saddle at the top of each tower and anchored at each end. As the wheel shuttled back and forth wire by wire, the cables slowly grew. It was an extraordinary operation, methodical, precise, and relentlessly demanding. Before the spinning could begin, workers had to build a catwalk, a temporary working platform spanning the full length of the bridge. These narrow, suspended walkways gave workers access to the cable path and allowed them to monitor and adjust the wire placement at every point along the span. Constructing the catwalks was itself a significant engineering task. The first wires had to be hauled across the strait by a Coast Guard vessel, with shipping lanes temporarily closed, then lifted to the tops of the towers by crane and secured in the giant curved steel saddles, each one weighing 150 tons. Cable spinning began in October 1935. The Roebling crew designed a split tram system, two spinning wheels working from opposite directions, meeting in the middle, to speed up what would otherwise have been an impossibly slow process. At peak productivity, workers were spinning more than 1,000 miles of wire in a single record-breaking shift. The wire itself was wound onto massive reels, color-coded to prevent confusion about which strand went where. 6 wires were spun simultaneously during some stretches of the work. The process had to be carried out in a precise sequence, carefully balanced across the cable geometry, to ensure that the finished cable would distribute loads evenly and absorb wind forces as the engineers had calculated. Working at the top of the towers meant spending hours in winds that regularly exceeded 45 miles per hour, nearly 800 feet above the water, in temperatures that could drop sharply without warning. The catwalks swayed in the gusts. The noise of the city and the ocean surrounded everything, and the work went on. By the time the last wires were in place, the 2 main cables contained a total of more than 27,000 individual wires. If those wires were laid end to end, they would stretch approximately 80,000 miles, enough to circle the entire Earth more than 3 times. The spinning was completed in 6 months and 9 days. Hydraulic jacks then compressed the completed wire bundles, 61 strands per cable, into the cylindrical shape of the finished cable, wrapping the exterior with a protective sheath of galvanized wire wound tightly in a continuous spiral. With the cables in place, engineers could begin hanging the vertical suspender ropes that would eventually carry the weight of the roadway. These steel hangers descended from the main cables at regular intervals, and connecting them required workers to operate at every height between the water surface and the top of the towers, often simultaneously. The complexity of coordinating this work across shifting weather conditions and with hundreds of workers in the air at once required a level of planning and communication that was extraordinary for the era. One of the most important innovations Strauss brought to the project was a safety net, a mesh of woven wire rope suspended beneath the entire length of the bridge during construction. The idea of protecting workers from falls with a net was not entirely new, but the scale of this one was unprecedented. Over the course of construction, 19 men fell from the bridge and survived because of that net. They became, informally, the members of something workers called the Halfway to Hell Club, a grim but defiant badge of honor worn by those who had fallen into the net and walked away. But the net could not protect against everything. On February 17, 1937, with the bridge nearly finished, a wooden scaffolding section collapsed. The weight of the debris tore through the safety net. 13 men fell. 1 jumped clear and survived. 2 survived the fall into the water below. 10 were killed. It was the single worst accident of the entire construction project, and it cast a shadow over the final weeks of work. In total, 11 workers died during the 4 years of construction, a number that, by the grim standards of comparable mega-projects of the era, was considered remarkably low. The roadway deck itself was the last major element to be installed. Once the suspender hangers were in place, prefabricated steel sections of the deck were lifted into position by crane and bolted together. The deck was divided into 7 separate sections, not because of structural weakness, but because of thermal expansion. Steel contracts in cold weather and expands in heat. Across a span of over 4,000 feet, even small temperature changes can cause significant movement. By dividing the deck into separate sections joined by expansion joints, a system of interlocking steel fingers that allow the sections to slide against each other, engineers ensured that the bridge could flex safely through California's full seasonal temperature range without imposing dangerous stresses on the structure. The roadway was completed on April 19, 1937, 4 years, 3 months, and 14 days after workers had first broken ground. On May 27th, the bridge opened to pedestrians for its inaugural day. 200,000 people walked or ran across the span. Children roller skated across it. 1 man crossed on stilts. Mayor Angelo Rossi presided. The mood was electric. A city that had spent years doubting and debating and arguing was finally walking across the thing it had built, and it was magnificent. The following day, President Franklin D. Roosevelt pressed a telegraph key in Washington, D.C., and the bridge opened to vehicle traffic. The announcement went out across the country on radio. The Golden Gate Bridge was open. The final cost had come in at approximately $35 million, over budget compared to Strauss's original estimates, but still a fraction of what earlier engineers had projected, and widely considered extraordinary value for what had been accomplished. The bridge had been completed ahead of schedule. It had claimed far fewer lives than comparable projects, and it had set a world record. At 4,200 feet, its main span was the longest in the world, a title it would hold for 27 years, until New York's Verrazzano Narrows Bridge surpassed it in 1964. But the engineering story of the Golden Gate Bridge did not end in 1937. It is, in many ways, a story that is still unfolding. The bridge sits between the San Andreas and Hayward fault lines, two of the most dangerous seismic zones in North America. When it was built, engineers incorporated flexibility into the design as much as their 1930s knowledge allowed. The towers were designed to sway. The deck was built to flex. But modern earthquake science has revealed vulnerabilities that Strauss and Ellis could not have known about. In particular, engineers discovered that the arch carrying the roadway over Fort Point, the old Civil War fortification near the South Anchorage, was potentially vulnerable to collapse in a major earthquake. A nearly $400 million seismic retrofit program was launched to address this, involving the installation of energy-dissipating devices throughout the structure, the replacement of approach ramp towers, and a series of extraordinarily precise lifts that transferred loads from the existing structure onto temporary supports, all without disrupting daily commuter traffic. Maintaining the Golden Gate Bridge is a continuous operation. A team of more than 100 full-time personnel is responsible for every aspect of the structure. The marine environment is relentless. Salt air corrodes steel, expanding and contracting temperatures, stress connections, and the constant vibration of traffic slowly works at every joint and fastener. The bridge must be repainted continuously, not in a single campaign, but in an ongoing cycle, with crews moving from section to section in a never-ending rotation. Inspection robots crawl along the cable interiors. Sensors embedded throughout the structure monitor deflections, vibrations, and stresses in real time. The bridge is, in this sense, alive with data. It carries roughly 10 million vehicle crossings each year. Since it opened, more than 2 billion vehicles have passed over it. It serves as a vital artery for commuters between San Francisco and Marin County, for freight moving through the region, and for the millions of tourists who visit the Bay Area annually, many of them coming specifically to see the bridge. The tolls that drivers pay, today collected electronically without toll booths, using license plate readers, continue to fund the bridge's operation and maintenance, just as they funded the original construction bonds that were finally paid off in 1971. There is something almost counterintuitive about what makes this bridge so enduring. It was built in an era of financial collapse, with hand calculations, hand tools, and manual labor on a scale almost impossible to imagine today. It was built by workers who were hungry, desperate, and sometimes terrified, suspended above a violent strait in conditions that would fail every modern safety standard. It was built by an engineer who, by his own admission, didn't fully understand the suspension design he was overseeing, who had to rely on colleagues and consultants to fill in the gaps his own knowledge couldn't cover. And yet it stands. Nearly 90 years after the last rivet was driven, the Golden Gate Bridge rises from the San Francisco fog as confidently as it ever has. The cables that were spun wire by wire in the winter of 1935 still carry the roadway. The towers that divers helped anchor to the ocean floor still pierce the sky at 746 feet. The international orange paint still catches the afternoon light the same way Irving Morrow imagined it would when he made his choice in a design meeting nearly a century ago. There is a principle in engineering that is easy to state and hard to achieve. The best structures eventually disappear, not literally but perceptually. They become so integrated into the fabric of daily life, so natural a part of the landscape, that people stop seeing them as achievements and start seeing them simply as the world. The Golden Gate Bridge has crossed that threshold so completely that its absence is almost impossible to imagine. San Francisco without it is not San Francisco. California without it loses something essential. The world without it is subtly but deeply diminished, and that, perhaps more than any technical specification or construction record, is the most honest measure of what Joseph Strauss, Charles Ellis, Leon Moisseiff, Irving Morrow, and the thousands of workers who built this bridge actually accomplished. They didn't just cross a strait, they changed what was possible. They proved that the most difficult engineering challenges, the ones the experts say can't be done, sometimes just need someone stubborn enough to try anyway. And then they built something the world would never forget.